In this video, we will talk about what it means for two propositions to be logically equivalent. So I want to begin with a definition which says that propositions P and Q are logically equivalent. So logically equivalent if they have the same truth table outputs. The same truth table outputs. And in that case, and we write, the way we write this is I say P, and then I put an equal sign with three sort of horizontal lines, Q. And I read that as P is logically equivalent to Q. So let's look at an example in which we determine whether each pair of propositions is logically equivalent. So part A has the proposition if P then Q, and the proposition if not Q then not P. So we've actually seen this second proposition compared to the first one in the previous video, or actually 2 videos ago I think. We gave sort of a Venn diagram explanation for why they are the same, but let's do this using truth tables. So I'm going to set up P and Q, and let's do a double vertical line, and on the right hand side I can set up P implies Q. So I'll build up one of these propositions, and let's also build up the other one. So for that one, I'll need to write not Q, not P, and then once I have those, I'll be able to build not Q implies not P. Okay, so let's separate each of these with a vertical line. So some vertical lines here. And now for Q, I alternate true, false, true, false. For P, I alternate double true, double false. And we've seen already how to form the truth table for P implies Q. It's only going to be false when P is true and Q is false. So that's the second row. In all other rows, this is going to be true. So not Q is going to be the opposite of Q, which is false, true, false, true. And then not P is going to be the opposite values of P, so false, false, true, true. So now I form another implication using not Q first, and then that's going to imply not P. So I'm looking at these two columns in this order. So it's only going to be false when the first part is true and the second part is false. So that is in the second row. And all other rows for this implication are going to be true. So if we look at this row and this row, they have the exact same truth value outputs. So the answer to this question is yes. Yes, they are logically equivalent since their truth table outputs are the same. Truth table outputs are the same. So let's practice using our notation for them being equivalent. So we would write P implies Q is equivalent to not Q implies not P. So on a conceptual level, that means these two propositions have the same meaning. We can use them interchangeably. So there's something important I want to note about the proposition not Q implies not P. This is a special name. It's called the contrapositive. The contrapositive of P implies Q. And in the next video, we're going to talk about contrapositives and also what are called converses and inverses more in depth. But I do want to introduce that term now. And we've actually seen a conceptual reason for why these two statements, P implies Q, why this is equivalent to not Q implies not, implies not P. But I want to recap that explanation. It involved looking at a Venn diagram. So if I write P implies Q, in words this means if we are in P, then we are in Q, Even though these are not technically sets that we're talking about, I'm going to sort of visualize them as being sets. Okay, so imagine that this is a set P. If we are in P, then we are in Q, means that P lies within Q. That'll guarantee that if we are in P, then we are also in Q. But now if we look at the contrapositive, which flips the order and puts negations on both of these, so not Q first, implies not P second. In words, that means if we are not in Q, then we are not in P. Then we are not in P. And that's also being represented by this picture. Because if I'm not in Q, it means I am outside of the Q circle. And if I'm outside the Q circle, then I'm definitely not in the P circle either. So this green sentence for the contrapositive is describing the same thing as the original implication. So both of these describe the same thing. This is a conceptual reason why they are equivalent. So let's do another part to this example, completely separate, where we test if two things are going to be logically equivalent. But for this one, I want to begin with some motivation for what the propositions are. So I'm going to start with the proposition, it is not, so I have this negation, it is not the case that in parentheses, I'm tall and I have black hair. So this is equivalent to something. It's going to be equivalent. I'm going to leave a little box because we'll fill the operator in here. Part of what's going to go here is if I negate this, I'm tall and I have black hair, it's going to involve something like I'm not tall, some missing word, and I don't have black hair. Let's space that out more. I don't have black hair. Okay, so I want you to pause the video for 1 quick minute to think about, well, what connecting word goes in that box? Think about this just logically and see, well, what word would go there? 4, 3, 2, 1. Pause it and try that for 1 minute. Alrighty, so hopefully you've done that. Hopefully you paused it and tried it for about a minute. So if it's not the case that I am tall and I have black hair, that's kind of like saying it's not the case that I'm both of these things. So that's equivalent to saying, well, I'm not tall, or, there's that keyword or, here's the symbol or, I don't have black hair. So we can generalize this by saying that this original proposition has the form negation, and then in parentheses P and Q. And this next statement has the form not P or not Q. So on a conceptual level, based on what we just did, it seems like these are going to be equivalent. So let's verify this using truth tables. All right, so let's draw P and Q. Double vertical line. Then I need to build up each of these. So for the first one, I'd have to do P and Q first. And then I can negate it, negate and get the negation of P and Q. For the next proposition, I have to negate P, I have to negate Q, and then I can finally do negation of P or negation of Q. So let's set it up again. Q is going to be true, false, true, false. P is going to be 2 trues, 2 falses. So the AND statement is only true when they are both true. So up here, in all other cases, it's going to be false. When I negate that, it's going to flip all of these. So this first thing is going to be false, whoops. And the rest are going to be true, 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 true. For not P, I got to flip P's signs, values. So false, false, true, true. For not Q, I got to do the same thing to Q. Flip them, false, true, false, true. And now I got to make an OR statement using these previous 2 columns, not P as well as not Q. So the OR statement is only going to be false when both of those parts are false. That's the top row. In all of the other rows, at least one of them is true, which makes the OR statement true. So if I look at these rows, here's one proposition, columns, here's the other proposition, they got the same values. So the answer here is yes. It is yes. And I should say something like, oh, these are the same. These are the same. So because of that, this proposition, not P and Q, is indeed equivalent to not P or not Q. Okay. So this is actually a very important and well-known equivalence. So I am going to highlight it. This is what's referred to as De Morgan's law in logic. So logic is very commonly taught in philosophy courses as well as math courses. And De Morgan's law is one of the very standard logical equivalences. I'm also going to go back, before I forget, and highlight the equivalence of an implication and its contrapositive. That is a super important one as well. And now let's look at one final example. So we have these two statements. I want to begin by giving you a chance to try this. So this time, pause the video for 3 minutes. 4, 3, 2, 1. Pause it for 3 minutes and try this. Alrighty, so hopefully you've done that. Hopefully paused it for 3 minutes to try this. This time, I need these three basic propositions, P, Q, and R, to begin with. And then let's slowly build through double vertical line. Let's slowly build these. Alrighty, so for the first proposition, I know I need P implies Q. And then from there, I can do P implies Q implies R. So we'll build up to it. For the second proposition, I will need not P. Then I can build not P and R. I will also need to get Q and R, which I'm ready to build already, because we'll already have Q and R. And then I can put these two things together and get not P and R, or Q or R. Okay, so let's start with R over here. Alternate true, false, true, false, true, false, true, false, true, false, and then Q double trues, double falses, so double true, double falses, double true, double falses, and then for P quadruple, so we'll do 4 of these, 1, 2, 3, 4 trues, and then 4 falses. If I had another letter, I would have to do 8 trues and then 8 falses and alternate like that. Alrighty, so let's start with this first implication. So this implication, remember, is only false if the first part is true, but the second part is false. So that happens in rows 3 and 4, where P is true and Q is false. So I read a false there. But in all the other rows, this is true. So let's write true in all of these other rows. And from there, I can form this next row. So this is another implication. The first part is the previous column, P implies Q. And the conclusion is R, which is this column. Okay, so for this implication to be false, the first part needs to be true, and the second part needs to be false. So let's see, that happens in the second row. First part is true, second part is false. Careful though. The first part is in this column, P implies Q. And the second part is in this column, R. Okay, so where else do I have a true first and then a false second? Well, that's here, as well as here. So the rest of these are going to be trues. So trues, 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 trues. Okay, now we get some easier ones. Not P. I just flip all the P's and make this 4 falses at the top and then 4 trues at the bottom. Now I got to do an AND statement with that and R. So let's see. For the AND statement, it's only going to be true if both not P as well as R, if both of them are true. So let's see, that happens in this row. They're both true. And this row, they're both true here. But in all the other rows, at least one of them is false. All right, so let's write some falses elsewhere. Falses in all of these other spots. And now let's do Q or R. So for Q or R, for this to be false, I would need both Q and R to be false. And that happens in this row, as well as this last row. But in all the other rows, at least one of them is going to be true. So I'll put a T. T's all around in those other spots. Okay, so now I have to form an OR statement with these previous two columns. And for an OR statement, it's only going to be false if both of these parts are false. So that happens here, as well as here. And all the other parts, at least one of the values is true, which will make the whole OR statement true. So let's put some trues in those. So now if we compare these two columns, they are a bunch of rows in which they have different truth values. For example, this is a false. Oops. This is a false. But this is a true, and that's different. Let's see, this is a true, and that's a false, so that's different. And this is a false, and that's true, and those are different. So the answer to this one is no. No, they are not equivalent. These ones are not equivalent, since their truth table outputs are different. Their truth table outputs are different. They are not all identical. They have to all be identical for them to be equivalent, but they're not here. So in terms of our goals for this section, we finished our second goal, to test whether two propositions are logically equivalent using truth tables.